Hello everybody. Uh, let's talk about chapter 6. And chapter 6 is talking about two new components, new passive components. So far we know only the resistor and sources. So here today we'll talk about the capacitor and inductor. So all the circuits that we have seen in all the previous chapters have this element here, which is the resistor, R. The side, of course, is the sources. And today we'll talk about inductor and capacitor. The inductor, the inductor is a coil. So it is similar to the resistor, but it has, it looks like a coil like this. So this is the shape of the inductor. Look like this. And the capacitor is two plates, two parallel plates. So this is how we how it look like. This is a symbol of the capacitor. The inductor is L, so like R, resistor, inductor is L, capacitor is C. And we know that the resistance is in ohm. This resistance is in ohm. The inductance is in H, or we call it Henry. So the inductance is in Henry, and the capacitance is in F, which is Farad. Farad. So here, as you see, we have three basic elements or three passive elements: resistor in ohm and represented by R, and inductor. So this is the resistor represented by R. So the resistor is R in ohm, and the inductor, which is a coil, and it is in inductance L, and it is in Henry. And then the capacitor has a capacitance C, and the unit is in farad. Ohm, farad, and Henry. R, C, and L. So let us see the properties of each one of them. So it is better, it's good that you need to, if you convert or just compare them, because they are actually, capacitor and inductor are opposite to each other. So if you want to draw, for example, this is a capacitor, this is inductor, here's inductor, and here's a capacitor. So again, the capacitor has a capacitance C, and it is in farad, farad, and the inductor has an inductance L, and it is in Henry. Then if we have a current in the inductor I, this current I, and same in the capacitor I, then we'll have a voltage across the inductor V, and the same for the capacitor V. So we can just add a note here that this is VC to say that this is a voltage across the capacitor, and this is IC is the current in the capacitor, and this is IL, which is the current in the inductor, and VL, which is the voltage across the inductor. As we know from chapter 2, we apply Ohm's law to find the voltage for the resistor, V equal I times R. And here, the relation is V times R. This is for the resistor, I times R. And there is some kind of similarity between resistance and the resistance and inductance. So this one is similar to this. So this is a starting point for you if you want to remember the relation between voltage and current in the inductor and in the capacitor. How? So we write almost the same equation for the inductor. So let us write it here. V, let's say this L, okay, equal L, and you can still write here I, L, I, L. So instead of IR will be L time I, L time I. But of course, this will not work because otherwise, if this has the same relations, then what is the difference between inductor and resistor? The difference is this simple dot. This simple dot. So VL equal L di by dt, which is I dot. Di by dt. VL equal L di by dt. That's it. This is the difference. So we know now for the resistance, V equal I times R, or R time I. For the inductor, V equal L I dot di by dt. This is the only difference. The capacitor is completely opposite to the inductor. Then if you want to find the relation for the capacitor, just convert everything. So if you have voltage, make it current. If you have current, make it voltage. Of course, if you have L, you have to make it C. Okay, so let us rewrite the same equation. V L I dot. V L I dot. But instead of voltage, we write V. We write current. Then it is I L. Let me write it here. I C. Instead of voltage, we make it current. And then instead of L, make it C. So this L will be C. And instead of I, the last one, instead of I, it will be V. So VC. So this will be the relation for between voltage and current in the capacitor. The relation between voltage and current in the capacitor. So again, we started with Ohm's law. But let us write it in different way. Let's say, for example, here, let's write it in any other different color, like this. V equal, instead of I times R, let us make it R times I. Okay? So let's erase this part. All of it. Okay, make it easy. So again, we start with the voltage. With Ohm's law. V equal I times R. Let us make I here and R here. There's no difference. The same. Okay, so this is Ohm's law. This is the law that we know. Then we repeat this in the capacitor, the inductor. So R will be replaced by L, and I will be I dot. I will be I dot. That's it. And then to convert the relation or to find the relation for the capacitor from the inductor, all what you have to do is to convert or change voltage, the voltage to current, and the inductance to capacitance, and IL to VC. This is supposed to be dot, sorry. So you have a dot here. I forgot this. Should have a dot here. Okay, let's make it in red. So again, instead of VL, make it IC. Instead of L, make it C. Instead of I dot, make it V dot. V dot. So this is a relation between voltage and current in the inductor and the capacitor. And you can rewrite this in integral way. How? Here you have a voltage in terms of current. Okay, you can find the current in terms of the voltage. And this can be done by moving L to the other side and then integrate both sides. Again, you move L to this side, the left-hand side, and then integrate both sides. Then in this case, we'll find IL equal 1 over L integration from 0 to T VL of T or VL dt. So this is the integral relation between the current and voltage in the inductor. Okay. Then if we know this one, we can find the relation for the capacitor. Then again, we apply the same steps. We have current here, IL, make it VC, of course. And then equal 1 over L will be 1 over C. And integration from 0 to T, you leave it as it is. And then instead of VL will be IC dt. dt. So this is the integral relation for the capacitor, which is very similar to the inductor, but just opposite. Okay, so here we know now that we have something called inductor, which has inductance L, and it is in Henry, and capacitor that has capacitance C, and it is in Farad. The capacitor, the inductor is a coil, which is similar to resistor, but it is a coil, not a zigzag line. The capacitor is usually two parallel plates. That's why it has this symbol here, the two parallel plates. Okay, to find the relationship between voltage and current in the inductor and capacitor, you start with Ohm's law. Start with Ohm's law. Ohm's law. Start with Ohm's law. V equal I times R or R times I. But and the only difference between this one and for the inductor is that instead of I, you make it I dot or di by dt. So VL equal L di by dt. And if you want to find the same relation for the capacitor, you change it from voltage. If you have voltage, make it current. If you have current, make it voltage. If you have inductance, make it capacitance. That's it. And you can get this relation. The second one here. This one. And if you want to find the opposite, if you, this one here, you have the voltage, you need to find the voltage in terms of current. If you want to find the current in terms of voltage, what you have to do is just move this move this L to the other side. To this side, then it will be 1 over L, and then integrate both sides. Same here. You move this C to the other side, will be 1 over C, and integrate both sides. You will get this relation here. And if you get any one of them, you can get the other one by changing current to voltage and voltage to current. And if you have inductance, make it capacitance, or capacitance, make it inductance. Okay, so this is the relation between voltage and current in the inductor and capacitor. What else we need to know about inductor and capacitor? The inductor L, this inductor stores energy. Inductor stores energy. Actually, both of them. And also the capacitor also stores energy. So these two elements are used to store energy. So they are like, for example, battery, for example, when you have a battery and you want to charge it, your cell phone battery. So imagine that this cell phone battery is a capacitor, for example. So you are charging it, then it will have you will store some energy inside it, and then you can use it when you unplug the cell phone, the charger. So the inductor stores energy. The capacitor stores energy. The inductor stores energy in terms of what? In terms of magnetic field. Magnetic field. Which is related to the current. When you have a current in the inductor, you create a magnetic field. So the inductor stores energy in terms of magnetic field, which is related to the current. The capacitor stores energy the same in terms of what? In terms of electric field. Not magnetic, electric field. Which is related to the voltage across the capacitor. Which is related to the voltage. In other words, we can say that the capacitor stores voltage. The capacitor stores voltage. And the inductor stores current. So in this case, you can say that the capacitor sometimes is acting as a voltage source, V source. So when you have a capacitor, you charge it. When you use it, it will act as a voltage source. The capacitor, the inductor, when you charge it and after that when you use it, it will act as a current source. Current source. Okay. So this is the second thing that you need to know about inductor and capacitor. First is the relation between voltage and current. Second is the behavior of this inductor and capacitor. The inductor stores energy in terms of magnetic field, which is related to the current. So we can say that it is actually storing current or act as a current source. The capacitor is storing energy in terms of electric field, which is voltage. So stores voltage, so it will act as a voltage source. So this is the inductor and capacitor again. What else you need to know is that in case of DC, So what's the meaning of in case of DC? If you have only DC sources, let's just leave this one here. Okay, so in DC, you can say in DC, for DC. DC means what? DC means you have only DC sources. So if you have a circuit that has capacitors and inductor, but it has only DC sources. DC means constant value. It's not a sine or cosine or triangular or whatever. It's not a function of time. Anyway, it's not a function of time. So if you have only DC sources, the capacitor, the inductor, is acting as a short circuit. So it's very similar to short circuit. So you can replace it like this. So if you have these 2 points here, so if you want to solve a problem that has inductor and has DC, you just simply replace it by short circuit. You replace it by short circuit. You replace it by short circuit. Very easy. And for the capacitor is just 2 plates. So in this case, you can replace it by open circuit. Makes sense. You have a capacitor that 2 plates. 2 plates are not connected. So it is actually open circuit. So for example, if these are the 2 terminals, all what you have to do is to replace it by just open circuit here. You don't have anything inside. That's it. So just open. Okay, so this is how you solve any problem if you have only DC and has capacitors and inductor. It will be very easy. All what you have to do is to replace the capacitor by open circuit and the inductor by short circuit. What else? If you have a number of inductors in parallel or series, if you have inductors in parallel or series, the inductor is the same like resistor. Same like resistor. Which means what? Assume that you have, for example, number of inductors in series. This one is 2 Henry. This one is 1 Henry. And this one is 3 Henry. Then what is the total now between these 2 points? This one and this one. For the resistors, if this is 2 ohm, 1 ohm, 3 ohm, you just add. That's it. For the inductor, also add. So it is 2 plus 1 plus 3. So if you have them in series, just add. So it will be 6. It will be 6. Very easy. And if you have inductors in parallel, like for example, assume that you have inductors like this. Then you apply the same method for the resistors. So assume that this is, for example, 3, and this one is 5. So what is the total here? The total is the multiplication over the summation. Multiply over the summation. So it will be 3 times 5 over 3 plus 5, which is 15 divided by 8. And if you have multiple inductors and all of them are equal, 1, 2, 3, 4, for example, and all of them are equal. This is, for example, is 8. This one is 8, 8, 8. Then the total inductance equal what? Equal 8 divided by number of inductors. So 1, 2, 3, 4. So it will be 4. 8 divided by 4, which is 2 Henry. 2 Henry. So these are the two special cases. Remember, in a resistor, if you have only 2 resistors, you multiply over the summation. And if you have multiple resistors and all of them are equal, you divide the inductance or resistance divided by number of resistors. Here you do the same, exactly the same. There is no difference. For the capacitor, it is completely opposite. Completely opposite, which means that if you have resistors, inductors in capacitors in parallel, you add. In parallel, you add. But in series, you apply the parallel rules. Okay, let's see. For the capacitor, assume that you have, for example, 1, 2, they are all parallel here. 3. You have 3 capacitors in parallel. And this one is, for example, 10. This one is 2. This one is 5 farad. Then what is the total capacitance? You just add 10 plus 2 plus 5, which is 17 farad. Okay, so you see here when you have capacitors in parallel, you apply the series. The series is to add. You know that. So if you have capacitors in parallel, you apply the series rule. So it will be, you add here. So it will be 10 plus 5, 10 plus 5 plus 2 plus 5. And if you have capacitors in parallel, in series, like for example, assume that you have these two capacitors here. 1, 2. This one is 3. This one is 5. Okay. Then here, the are in series, you apply the parallel. Okay, so as if you have two capacitors in parallel. Okay, as if you have two resistors in parallel. That will be 3 times 5 over 3 plus 5. Okay, which is whatever here, 15 divided by 8. You see here, you have, in this case, this one here, you have the two in series, and you apply the parallel rule. Here, this one, you have them in parallel. You apply the parallel rule. So the inductor is very exactly the same like resistor. But the capacitor is opposite. You apply the series rule, the parallel rules when they are in series. Here they are in series. Okay. And if you have a number of capacitors in series, like this, and all of them are equal. Again, this one is 8 farad, 8 farad, 8 farad, 8 farad. They are series, okay? Then you apply the parallel rule. The parallel say what? If these two are in parallel, they are all equal, then it will be 8 divided by number of capacitors 1, 2, 3, 4. Divided by 4, that is that's 2 farad. So this will be another thing that you need to know. What else you need to know about the capacitor and inductor? I believe maybe there's only one thing. That is, we are interested in the energy. As I said before, the inductor is storing energy, and the capacitor also stores energy. The inductor stores energy in terms of current, magnetic field, which is related to the current. The capacitor stores energy in terms of voltage or electric field. Then, just a moment. So the inductor and capacitors are storing energy in terms of current and voltage. Then we are interested to know what is the total energy. We need to know what's energy stored in the inductor and capacitor. So let us see what is the value of the energy. The energy is called W. Let's say call it WL, for example, and for the capacitor is WC. Okay. For them, they are very similar. 1/2 for the inductor, 1/2 L, so it is related to L for sure, and it is storing current, so it is IL square. So this is the energy stored in the inductor, is 1/2 LIL square. And for the capacitor, it is 1/2 what in this case? You can tell me, I believe, that you just need to change this L to C and the current to voltage. Okay, this is what we did before. So it will be C VC square. So this here summarizes all what you need to know about the inductor and the capacitor, starting from the symbols for both, the units, inductance is in Henry, capacitance is in farad, the relationship between voltage and current in both. What is the inductor, the current and the capacitor? The inductor is storing energy in terms of watt, and the capacitor doing what? In case of DC, what do you have to do to solve any problem? You need to replace the capacitor, the inductor by short circuit, and the capacitor by short circuit, by open circuit. This is the inductor by short circuit and the capacitor by open circuit. And if you have multiple inductors or multiple capacitors, how do you deal with them? For the inductor, they are exactly the same like resistors. For the capacitors, they are similar, they are opposite to them. Okay. And the last thing here is what is the amount of energy stored in the inductor and what is the amount of energy stored in the capacitor. So let me stop here and then we'll continue next time.